Hi, and thanks for tuning into our video presentation of our paper, Bridging Discrete and Continuous State Spaces, Exploring the Ehrenfest Process in Time-Continuous Diffusion Models. This is shared work between me and Lorenz Richter, as well as Manfred Opper. The general setup we consider is generative modeling with stochastic processes. And the idea of this approach to generative modeling is to transport samples from a prior measure to a target measure with a stochastic process. The key concept here is the time reversal of a stochastic process. And we can visually show this with a picture of Paul Ehrenfest on the far right side, which is slowly transformed into pure noise with a stochastic process. Now, generative modeling reverses this process to turn a picture of pure noise into, for example, here as a sample of Paul Ehrenfest. But more generally, as I said before, we want to link two measures. And this is here shown with the second row, where we have a tractable distribution in the form of an E, which we transform into a Gaussian and back. Stochastic processes can be considered in time and space, and they can be both discrete and continuous. And so in 2021, Song et al. Make the connections between continuous state space stochastic processes in discrete time as a Markov chain and continuous time as an SCE. Our work will make another connection between discrete state spaces and continuous state spaces in continuous time. Now, discrete data is fairly widely distributed, and the potential applications of discrete generative models are manifold. So for example, pictures in their digital form are stored in a computer as discrete signals, but also you have more fundamentally discrete data structures, such as graphs or biological data, such as discrete sequences, but also text, for example, which is also a discrete sequence. And as I said earlier, we have a stochastic process, and in the case of discrete data, this is a Markov jump process. And as also said earlier, we have two processes, in fact. We have the noising process, which is a stochastic process which noises the data slowly. And this is characterized by the rate function, RT, which denotes the jump probability of the process M from the state Y to the state X. And the probability of that movement can be written down as an analytical function. Now, in the center of this slide, we have a picture, a visualization of a Markov jump process. And here we can see that the states are discrete, but the time is sampled stochastically, and thus we have to consider time as a continuous variable. In generative modeling, we also have the denoising process, and this is again a Markov jump process. And all the characteristics and attributes of a Markov jump process hold as well as above with the noising process, but we have different rates, and these are the backward rates. Now, for two states, X and Y, the transition rates of the time reverse process, M, going backwards in time, is given by the expectation over the initial condition X naught of the two distributions of X and Y given X naught. So this is the ratio. If you multiply that with the forward rate, you will obtain the reverse rate. Now, the conditional expectation above can be compared to the continuous case where we can define the conditional score. And this leads us to our conjecture, namely that the rate and the score functions play analog roles and can be related to each other. Now, for a general process, we can define a regression loss. So we train a neural network with a regression loss to learn the conditional expectation over a given expectation. And if that model is trained sufficiently, and it is important to say, note that this regression loss holds valid for any Markov jump process, we can then simulate the reverse timed Markov jump process with the SAD function approximator. But now we want to highlight that there's a particular stochastic process, namely the Ehrenfest process, which acts as a very convenient intermediary between discrete and continuous state spaces. And for that, Lorenz will tell you more.
So I'm going to tell you about the Ehrenfest process now, which is defined as following. So it's essentially a sum of capital S very easy processes, and these processes live on the state space 0, 1 and have the very simple transition rates of basically 1/2 for switching either of the states. And yeah, if you look at the sum of these easy processes, you can easily realize that the Ehrenfest process is a birth-death process with the following transition rates here. So birth-death means that you can only basically jump one step up or down if you want, right? And you can already see that the transition rates depend both on the system size S and the current state X. The Ehrenfest process has a couple of nice properties. The first one is written down in this lemma here, where we basically realize that we can very easily sample the process without needing to sample trajectories, actually. And it's illustrated as follows. So basically assume that you start in the data point x0. Then you can write this Ehrenfest process at time t as a sum of these two quantities. And both quantities are just binomially distributed with certain parameters as written down here. And the key observation is that we can basically, we know these parameters, and we can basically very easily sample by just sampling binomial random variables and add these quantities. It then also follows immediately that we know basically a closed form solution for the forwards conditional transition probability. And this, as you probably guessed already, is also very much analog to the Ornstein-Uhlenbeck process that we consider in time continuous and space continuous settings. So now we want to make this connection even more precise by looking at the scaled Ehrenfest process, which now lives on this omega here. So basically what I do here is I kind of center the Ehrenfest process around 0, and I scale it with 2 divided by square root of S, where S, as you recall, is the system size, basically. And this implies that, looking at the omega here, is that basically my space gets bigger and bigger, but also finer and finer. So the increments get finer and finer. And this is actually nothing new. This has been studied already roughly 20 years ago and has been shown very rigorously that if you take the limit of the state space size S to infinity, then the scaled Ehrenfest process converges in law to the classical Ornstein-Uhlenbeck process as written down here. Right? So this is a quite nice connection, which can be proved very rigorously. And we illustrate this here with some numerical realization. So basically here is a numerical realization of the Ornstein-Uhlenbeck process, and on the right-hand side for the Ehrenfest process. And here it has basically 3 states, so S is 2, and I basically increase the state space size. And while I do that, we see that we kind of get closer to what we expect, namely the Ornstein-Uhlenbeck process. Okay, so now we want to also study the state space limit of the time reversed process, because this is what we are really interested in generative modeling. And we can do this by looking at the so-called Markov or so-called jump moments of the Markov jump process, which are defined as follows. So it looks a little bit like the mean and the variance, if you want. And if we do that, then we can basically look now at the first and second jump moments of the time reversed scaled Ehrenfest process. And we can basically derive formulas for this. So these we denote here with B arrow and D arrow, and we can relate them to the jump moments of the forward process, B and D. And then here's an additional term, which is again a conditional expectation, which might not be surprising. And inside the conditional expectation, we have, as defined here, some kind of finite difference between the forward transition probabilities. And you can already kind of get the intuition that, this guy in the limit S to infinity converges to the ordinary derivative. And well, since we have here a ratio, this whole thing might probably converge to the gradient of a logarithm. And then there's some little O terms here, which of course vanish when S goes to infinity. So as I already hinted at, the previous proposition implies that the scaled time reversed Ehrenfest process is expected to converge in law to this process here. And yeah, if you look carefully, you see that this is exactly the time reversal of the Ornstein-Uhlenbeck process that we had before, because here we see the famous score function appearing. So this is a nice observation where we basically have exactly related the Ehrenfest process, or in this case, the reverse Ehrenfest process, to the reverse Ornstein-Uhlenbeck process. And this observation allows us now to directly link these two settings, namely to directly link the state discrete setting to the state continuous score-based generative modeling setting. And basically this formula here shows how we can do this. Namely, we can relate this conditional expectation, this is the one we had also a couple of slides ago, to the score function in the state continuous setting. And this is a quite nice observation because it allows you basically to directly relate these two settings and to carry over methods from the one setting to the other setting. In particular, it allows for transfer learning. So now I can basically say I take any trained score that I find in the internet that people have trained in the continuous setting, and I basically use this as a plug and play estimator for my discrete setting of the conditional expectation here. Right? So this is one implication, that the connection to the Ehrenfest process allows for transfer learning. But also it allows us to motivate new loss functions, basically coming from this connection to the continuous case. And yeah, we just wrote them down here. You don't have to understand the details now. It's maybe a bit too detailed. You can read the details in the paper. But essentially what we want to show here is that only with this connection to the continuous setting, we can come up with these loss functions, which might have nice properties which we will see in the numerics. Speaking of numerics, let us start with a first illustrative example in D being 2, so 2-dimensional, and 32 states, or actually 33 states, where we basically have a tractable example. So we know the target distribution, which is this E here, E for Ehrenfest, of course, and we trained here the time reversal using these different losses we had before, and we see that indeed it's happening as expected, that we kind of can reach the target distribution with the time reversal idea. We also looked at some more complicated problem, namely at the Cypher 10 data set. And what we did here is we, on the one hand, trained our Ehrenfest model from scratch, which with these different losses here, so you can read the details in the paper. And we compared these scores here, which are typical for generative modeling. And when you look at the scores and compare them to alternative discrete models, we can see that even without actually a lot of hyperparameter tuning, we could partly improve on the metrics. I mean, it's always a bit difficult to decide on what metric you look, but this is a quite good performance. You also see some images here on the left-hand side. But what's also interesting is this Ehrenfest transfer learning, where we basically just copied a model from the internet that was trained on the state continuous setting, and we just plugged it in, and out of the box we got pretty good performance for this discrete model. So this really happened without any further training on our side. So now you can basically take any continuous model you find in the internet and make it discrete with the Ehrenfest process out of the box. Yeah, so with this, we would like to conclude. And so what we have done is we have proposed a new loss function that was motivated via conditional expectation for training state discrete diffusion models. We have essentially introduced the Ehrenfest process and derived the corresponding jump moments for its time reversed version, such that now, for the first time, we can link score-based generative modeling to time continuous discrete processes. And this is quite nice, as we think, because it allows that one setting can benefit from the respective other by, for instance, coming up with new loss functions, transfer learning, noise schedules, etc. And we hope that more connections will evolve in the future. So with this, thanks a lot for listening. Please don't hesitate to write us an email if you have any question. You can find the code online, and see you at the conference.